In this example, we will antidifferentiate the given rational function. The key observation to make is it's degree 4 over degree 3. So it is an improper rational function. And that requires us to start off with a polynomial log division. So we need to take the x cubed minus 3x squared and divide it into x to the 4th minus 5x cubed plus 6x squared plus 18. So we ask ourselves, x cubed multiplied by what will give us x to the 4th? The answer is x, so we subtract away x multiplied by the x cubed minus 3x squared. So we're subtracting away x to the 4th minus 3x cubed. So minus 5x cubed plus 3x cubed is minus 2x cubed plus 6x squared plus 18. X cubed times minus 2 will give us that minus 2x cubed. And now we need to subtract away minus 2 multiplied by this quantity x cubed minus 3x squared. So we're subtracting away minus 2x cubed plus 6x squared, which leaves us with a single 18 left over. So putting this together, what this tells us is that the quantity x to the 4th minus 5x cubed plus 6x squared plus 18 can be expressed as x cubed minus 3x squared times x minus 2 plus the remainder term 18. And thinking about what we want to integrate, that quartic polynomial divided by this cubic x cubed minus 3x squared. Let's divide each term by that quantity. When we do so, on the first term on the right simply becomes the polynomial x minus 2, and the second term is 18 divided by that cubic, x cubed minus 3x squared. And this is exactly where we want to be. Whenever we start with this improper rational function and we perform a polynomial long division, the goal is to rewrite it as a polynomial plus a proper rational function, something that we can apply a partial fraction decomposition to. In order to write out the form of the partial fraction decomposition, note that the denominator factors nicely as x squared times the quantity x minus 3. So to perform the partial fraction decomposition, we have 18 divided by x squared over x minus 3. So x squared is a repeated linear term. So a over x plus b over x squared. And x minus 3 is a single linear term. So c over x minus 3. At this point, we take the denominator on the left and we multiply both sides of the equation by it to clear up fractions. That leaves an 18 on the left, and on the right we'll have a multiplied by, now one of the x's cancel, so x times x minus 3. Plus in that next term, both of the x's cancel, so b times x minus 3. And in the last term, the x minus 3 cancels. And at this point, it's beneficial to plug in a few intelligent choices of x to see if we can immediately solve for some constants. And we note that if we plug in x equals 0, the a term and the c term will both vanish. So if x is equal to 0, our equation becomes 18 still on the left is equal to b times minus 3. So immediately we know that b is equal to the number minus 6. Additionally, if we plug in x equals 3, the a term and the b term will both vanish, and we can solve for c. So if x is equal to 3, 18 is on the left, and we have c times 3 squared, so c times 9, and c must be equal to 2. So in order to solve for that constant a, we'll just go ahead and algebraically expand on the right so that we can set up enough equations. Here it's just going to be one equation to solve for that a. So we have an a plus c x squared, a b minus 3a x, and a minus 3b. And if we equate together what would be the coefficient of x squared on the left and the coefficient of x squared on the right. So on the left, whether we have it written down or not, there's really a 0x squared. So we know that 0 on the left has to be equal to that a plus c for the coefficient on the right. So a plus c equals 0 tells us that a is equal to minus c, which is equal to minus 2. So now that the algebra is taken care of, we can do the easy part in this problem, which is evaluate the antiderivative. Okay, so I've kind of cut and pasted our work from the previous slide, and what we'd like to do is just go through and anti-differentiate term by term. So we have the antiderivative of x minus 2 minus 2 antiderivatives of 1 over x minus 6 antiderivatives of 1 over x squared plus 2 times the antiderivative of 1 over x minus 3. So term by term, we have 1/2 x squared minus 2x. The next antiderivative of 1 over x is natural log absolute value x. Here, be careful to note that the antiderivative of 1 over x squared is minus 1 over x. So that minus a minus becomes a positive, 6 times 1 over x, plus 2 natural logs absolute value x minus 3. So as we've seen with partial fraction decompositions and integration rational functions in the past, many times the algebra in the beginning can be the most time-consuming portion, but once you get through that algebra, hopefully the resulting antiderivatives will be extremely reasonable to evaluate.